Hi everyone, welcome back to our first episode of Space Store Live of the year. I hope everyone had a good Christmas and New Year. There's been lots of exciting stuff happening over the festive period in space news. So Nick and Terry are going to be bringing you lots of great stories, as well as what to look up for in the night sky in the upcoming weeks. thank you for taking your time out of your evening to join us, and I'll now pass over to Nick and Terry to get us started.
Cheers, Abby.
Right.
At least we're not clashing with the World Cup anymore. We were clashing with all sorts of stuff in December last year. Yeah, as Abby said, hope we've had a really great Christmas. We're a bit late to talk about Artemis because it's like done and dusted now, but really pleased that they had a very successful kind of completion to the mission with very few failures, unlike our opening story, which was putting it mildly, a bit of a shame / fiasco, depending on your point of view. And obviously, it's a real tragedy for the scientific community and the engineers who've worked long and hard on a lot of the payload and the systems integration and the satellites themselves. But yeah, we're going to talk about Virgin Orbit and what happened, because as we said in the title there, space is hard. And it is genuinely quite difficult. You only have to go back to the early days of Apollo, when and Mercury even, when they were launching rockets and blowing them up on the launch pad, and the various press were calling it Kaputnik. And then moving forward, obviously we had two tragedies with the space shuttle. Thankfully in a lot of modern cases now, human beings haven't been involved in some of these disasters, but even SpaceX in the early days with the Falcons, when they were trying to land them back especially on the floating platforms, they were having an absolute mare of a time trying to get them to stick onto the floating platform. So that was, it kind of precludes, as it were, or kind of leads into Virgin Orbit. And what they're trying to do is really quite complex. I mean, obviously, as you can see in the image, they've got a 747. They've got basically a 50-plus-year-old aircraft, which they're strapping a rocket to the underside of. Much in the same way that the NACA and burgeoning NASA and experimental aircraft were in the late 1950s, early 1960s with the X-15. And then essentially take off from a conventional runway. So in this case, it's a runway in Cornwall, which is in the southwest of England, if you're listening from overseas. Taking off, flying over the North Atlantic, basically off the southern coast of Ireland. Finding a nice clear patch. Hopefully there's no shipping or anything anywhere nearby of any aircraft. Dropping said rocket. And then that basically fires and goes off into space, or doesn't, as the case may be with this one. So the Newton 4 rocket, basically it's a multi-stage system, drops. You've got a first stage burn, which takes it up to a certain altitude, separation, what's called SECO, second engine cutoff, second stage burn, etc. before that, and then fairing deployment, which is basically where the satellites are in the front of the nose cone. It's called the fairing, and basically that will then kind of separate the shell for that which is protecting the satellites, and then hopefully the satellites will go into orbit. What it looks like happened at around about 180 kilometers up. This is what Virgin preliminary findings are saying, is that they had a failure. Now, you'd think 180 kilometers up, that's quite high. I mean, that's way above the Kármán line, that's into space, but it's not into an orbital insertion point, which is what they needed. Now, the spacecraft's called Cosmic Girl. The mission was called Start Me Up. And if you remember the famous song by the Rolling Stones, you start me up, you never stop. One of the lines in that is, you make a grown man cry. And I can imagine there are a lot of scientists and engineers who are doing exactly that. You had 2,500 people turned up to Cornwall, which was an amazing, apparently the live event itself, when you were there, was really, really good. The one thing I have to say, and this was not just me saying, this is all over social media, this is all over every commentator pretty much that watched it, was their social media feed and their kind of webcasts were nigh on abysmal. So a lesson there is not only the rocket needs to get into orbit, but Virgin, being a communications company, controlling a lot of the internet, especially in the UK, Virgin Mobile, Virgin Media, etc., do an awful lot in terms of communication. You'd have thought that they got people who actually knew what they were talking about covering the launch, which they clearly didn't. They rolled out the Bays Minister, Grant Shapps, and again, it was all a bit of a fiasco, because at one point Virgin was saying, yes, we've achieved orbit, and then like 20 minutes later they said, oh, actually we haven't. Possibly the reason for that is the telemetry, which is the data coming down, the data link coming down from the rocket and all the satellites. So when the satellites go into orbit, they transmit data down, and you can get all sorts of things, such as the battery status, the health of the satellite, temperature, etc. That's what's known as telemetry data. The telemetry from the rocket as it was launching up was completely all over the place. It was an absolute mess. At one point, the rocket was breaking basically the galactic speed limit. It was traveling faster than the speed of light and had exited the solar system. It was just insane. Now, given that the UK space sector employs 47,000 people, this is not an indictment on the UK space sector as a whole. UK space has been doing phenomenal things for decades in terms of satellite design, satellite integration, satellite building, instrumentation. It's been amazing. But launching rockets, in the early 1970s, you had Black Arrow, which was launched from the Woomera test range in Australia, which was the UK's only official launch into space, which then Callaghan, no, it wasn't Callaghan, it was one of the, I think it's the Labour government in the early 1970s, cancelled that program. This is hard, and what's making it harder in terms of the kind of ongoing forecast for Virgin Orbit is because of this, and they're already struggling anyway in terms of their cash burn through. And you look at any of the kind of financial websites, they're struggling financially massively. So when they were initially kind of listed, as it were, the company were valued at over $3.65 billion. After this disaster, their market capitalization dropped to $654 million. That's a drop of nearly 2.7 plus billion dollars from their market capitalization. And as I said, their cash burn rate is extremely high. Their share price collapsed by, I think it's 23% overnight. And there's some serious questions being asked now about ongoing investment. Now, as I said, this is not a criticism at all of Spaceport Cornwall. The great team down there, they've been doing great stuff. But the other thing is that the UK is kind of, I don't know what the government were thinking, but they were playing it as almost like a kind of Brexit card. It's like, oh, we've beaten the Europeans into space, and the French was just saying, well, hold on, we've been launching from French Guiana, using Ariane satellites for about 40 or 50 years. What do you mean you've beaten the Europeans? It was ridiculous. I've just been told my microphone's a bit too close. It's not the case that we've beaten anyone. This is a really difficult thing to do, and close cooperation with multiple European partners and getting people like the European Space Agency on board with the potential for launching from European soil is really, really important. So playing this whole political stupidity card to me again was ridiculous, given that the cost to orbit now has reduced so much. Even 10 years ago it was $20, $30, $40, $50,000 per kilogram to get something into orbit. Now it's a couple of $1,000 up to maybe about $5,000 per kilogram on the Virgin Orbit mission. It's a real shame, because the impact that this has had, again, from social media, from the feedback, in the scientific community, everyone recognizes and realizes that this is difficult. It's a problem. They will rectify it. They're already having their kind of post-flight analysis debriefs. They've talked to their various customers about the insurance issues that are now facing. That's the other thing, because it's failed. The insurance costs are going to go up as well. Thankfully, everyone was insured. And don't forget, there were 9 satellites on this. So 7 of them were civilian, 2 of them were military satellites. So, the Ministry of Defence, for example, so I'm doing some work on this area at the moment, are heavily invested in UK launch and having sovereign capability. I always find it a little bit laughable that they call it sovereign capability, because Virgin Orbit are a US company. The aircraft is a US-based and registered aircraft. The rocket launcher is US-based. The fueling system is US-based. And the command and control is US-based. Obviously, the satellites are being developed here, and having the ability to take off from UK soil gives you that complete picture, as it were. But now you've got, obviously, Scotland, and even today, some massive issues happening in Scotland in a completely different area, but issues that are effectively fueling the fire for Scottish devolution, when 80% of the launch capability that this country is going to have is going to be in Scotland. There's some serious political games going on here, and I don't know what you think, Terry, but it's worrying, I think.
Yeah, I agree with everything you're saying. Yeah, there are 2 points that sort of struck me. It shows you how important downrange safety is, because even though it got up, as you say, into space 180 kilometers up, that stuff all came back down again. Yep. Unfortunately, it was over the South Atlantic, presumably still within the exclusion zone, or at least people would have been aware.
No, it wasn't.
It was beyond the exclusion zone.
It came down from the videos I saw. Some people were filming it coming down off the coast of Tenerife, so it was kind of mid-North Atlantic.
Yeah,
so,
yeah.
But yeah, it's range safety is a big one.
And then if you're launching north from Scotland, which is the other option for the UK, as opposed to a horizontal plane takeoff launch from Cornwall, you're also going up into an area there that has quite a lot of activity, a lot of fishing trawlers, a lot of military stuff, with the Russians coming around the North Cape and down into the Atlantic. Americans, I'm sure, active up there too. So it just shows you there is always a risk, and it's why you don't normally launch over land. Like in Australia, you're mentioning Wimmera there. That's basically in the middle of the Australian desert. But if stuff had come down several hundred miles downrange from the Wimmera launch, it could still have been in an area where there are possibility of casualties. So yeah, as you say, space is hard. And if you go back even before the early Apollo failures, right back to the beginning of the American spacecraft space program, all you saw were rockets blowing up on the pad or getting up, 50 or 100 feet and coming back down in a fireball. So it's not easy. You could say, well, we've had 50, 60, 70 years of experience of launching rockets now. So we should have ironed out most of the problems, but you only get one chance. If something goes wrong, that's it.
Well, that's the thing. I mean, the velocities we're talking about here, you're looking at 11,000 mile an hour escape velocity to get into orbit. Then once you're in orbit, these are things moving at 17,500 miles an hour around the Earth. And the slightest failure, when you're looking at fuel injection systems and fueling systems that are using hypergolic fuels, potentially that, they're explosive on contact anyway, any number of things can go wrong. So it's a shame, and it looks like Virgin are possibly scheduling their next attempts towards the end of 2023. And that again brings back the question of cadence. You look at SpaceX, and we've all got our issues with SpaceX, and they're brought into the fore again because of what's happening in Ukraine, and now they're saying they're going to turn Starlink on for Taiwan, and all. So there's all sorts of political ramifications there. But SpaceX have nailed it in terms of every time now they're getting the rockets into orbit pretty much, even the Falcon Heavies. There's a Falcon Heavy launch only a few days ago. This is a big, really complex spacecraft, and then landing 2 of the 3 cores back on the surface of the Earth, literally in parallel. It's a technical achievement that you can't knock. And as you said, yes, it is hard, but he seems to have got over that now. And he's still got space, Starship, etc., to kind of get ready and launch. And you only have to look at Artemis and look at the delays on that, the safety aspects of that, and the number of times that they said no, we're not going to launch, and we're going to go back to the pad, and we're going to reconfigure, and we're going to change. It almost seems like this could be, especially in the current economic climate where we've got a major cost of living crisis. And yes, the UK is a burgeoning space economy. Don't get me wrong. There's a lot of job potential. There's a lot of economic potential in terms of space. But maybe this is almost a bridge too far, to coin a phrase, as it were, in terms of we've got everything else. Yes, it'd be nice to have launch capability, but don't forget any launches from Scotland are not going to be into equatorial orbits, which is where a lot of satellites go. They're going to be into polar and sun synchronous orbits, which, yes, is very important for Earth observation, for defense purposes in particular. It's very important. I don't know what's going to happen with this in terms of, Virgin Orbit. As I said, their financial situation, you only have to look on, any number of financial websites to see just how precarious their financial situation is. On saying that, SpaceX were also, and Tesla, big companies have been teetering on the edge, all through their history. So let's hope that they can pull this back. Let's hope that future missions will be successful. I think, the first attempt, yes, things can go wrong. If it fails again, there's going to be some serious questions asked, I think, and that's the thing that I guess nobody wants to see, because there are jobs being created in Cornwall. There's a lot of education and outreach. As I said, the only thing they need to get right, apart from the spacecraft itself, is their comms. Their comms was beyond abysmal, and I'm not just saying that. I've sat through European Space Agency launches. I've sat through Ariane promotional videos where literally the entire audience has fallen asleep. They're not the worst at it, but they're close. You only have to look at SpaceX, and we were saying just before we went on air just how good SpaceX are. Hate them, love them or hate them, they are absolutely brilliant at getting people on side, and this is why they almost have that Apple style cult following where you can't say boo. I mean, Elon Musk has dug himself into a massive hole over what he's done with Twitter, and his whole stance on working 19 hours a day, 7 days a week, all of that side of things. But you can't argue with the fact that his comms team and from the space side, they've nailed it, and they're getting huge contracts, and everybody wants to launch with them. So The funny thing is, you could have grabbed all of these satellites were pretty much put on the Virgin Orbit rocket, were small. They were compact CubeSats, some of them 12U CubeSats. You could put all of them in a Peli case, fly them to the United States for a few £100 and launch them from the US. It would have been cheaper. So, and probably more reliable. You could have put them in the fairing on a SpaceX rocket. Anyway.
Yeah. The other thing is, of course, they'll have taken a big hit. Those would have been insured, but their insurance premiums for the next launch won't have gone down.
Oh, this is the thing.
Gone up.
Yeah, this is the thing. The only people who rub their hands together in glee, we talk about space debris a lot on the show, and the looming problem, and it was talked about in Room magazine. There's a whole section of one of the big space magazines just devoted to the whole problem, the growing massive problem of space debris. But the only people who are rubbing their hands together with regard to that are insurance companies. Yeah. Are thinking, well, yeah, great. Anyway,
yes, let's be a bit more optimistic.
Yes.
Yep. Good old JWST strikes again. This is a fascinating story. It goes back well before James Webb, but we'll come to that in due course. These are fascinating objects that I have to admit I had never heard of before. Green pea galaxies. They were first discovered by the Sloan Digital Sky Survey back in 2009. And as the name would imply, they're green, they're small, they're round, and in most images, they're unresolved, which is why they're more like a blob than a pea. And they appear green, which is very unusual in terms of looking at a galaxy, because the light in them is emitted specifically at certain wavelengths rather than over the whole spectrum of light that you get, say, when you look at the Andromeda Galaxy, which is basically sort of whitish because it is the light from billions upon billions of stars, from very hot blue-white ones to ones like the Sun, down to and red giants like Betelgeuse, red supergiants, and smaller red stars. So the overall picture of your normal galaxy is basically fairly white. There may be very bright blue patches in it or very bright red patches in it, but overall, the light coming from a galaxy is usually pretty white. Not these ones. If you see the images in close-up, they really are spectacularly green. And that's because they're only emitting light very strongly, much more strongly in the green and slightly bluish-green range of the spectrum than anywhere else. And they're very rare. They only constitute about 0.1% of all of the nearby galaxies. And until the James Webb came along, we really didn't have any images of any that are very far away. So 0.1% is obviously pretty small in terms of the total percentage. They're also very small. The average diameter is about 5,000 light years, and you compare that with the diameter of the Milky Way, which is about 100,000 light years, which is considerably bigger. So the main interest in them is, why are they showing this very intense bright green color? And the reason for that is they're extremely active in star formation. They are creating stars at a much higher rate than your average galaxy. And the bright clouds that we see are basically the light emission from the gas that's being activated by this very, very high rate of star formation. So we knew about them. A relatively few number were discovered before, as I say, in the Sloan Digital Sky Survey. But along comes James Webb Space Telescope with its vantage point up in space and its incredible resolution and so on. And what they did was they looked for galaxies away beyond the near the edge of the observable universe, ones that have been gravitationally lensed by a huge star cluster called SMACS, SMACS 0723. And if you saw that very famous early image from James Webb Space Telescope showing the gravitational lensing, these little green pea galaxies show up. Now, if you look closely in that image, they're not green, they're red. And the reason is very simple: redshift. These are about 13.1 billion light years away. when the universe, we're seeing them as the universe was only about 5% of its current age, and the light has simply been redshifted so that it's in the red end of the spectrum, and that's where James Webb specializes. In fact, they were imaged by the near-spec image, the spectrograph, which operates in the infrared. We knew that they were green pea galaxies, even though they appear red, because we would allow for the redshift, but also because they show the light of certain elements which you get only in these green pea galaxies of that length, or that strength: oxygen, hydrogen, and neon. So the spectra indicated, or more or less confirmed, that they were these green pea galaxies, but very, very far away, and excuse me, shifted well into the red end of the spectrum. Now, the interesting thing is, why are these galaxies having such an unusual concentration of those elements? For example, the oxygen is only about 20% of the ratio in the Milky Way, and one of them is even less than that. And the reason is that these galaxies are so young that they are mainly composed of the primordial elements that were there from the Big Bang, which is mainly hydrogen, helium, a little bit of lithium. The other elements that astronomers call metals, which basically everything heavier than lithium, they are created by successive generations of stars burning through their life and creating the heavier elements, and then blasting them out into space, where they then become caught up in giant gas and dust clouds and form successive generations of stars. Like our sun is probably a fourth generation, maybe fifth generation star, contains a lot of other elements, not just hydrogen and helium. But these very, very young galaxies should not have had, and don't have, in fact, very many elements other than the very primitive elements that were there around the time of the Big Bang. So one of them, in fact, it turns out to be only have only about 2% of the proportion of the oxygen in the Milky Way. And oxygen, believe it or not, is classed by astronomers as a metal. As I say, they class anything that's heavier than lithium as a metal, which means that these are the galaxies basically that are the most primitive in terms of the composition, the element composition that we have ever discovered in the universe. Very, very few of the heavy elements, mainly hydrogen and oxygen and some neon. So this one in particular, I don't have a note of the actual number, it's just a catalogue number, is reckoned to be the most primitive, chemically primitive galaxy that we have ever discovered. Now, we can't say very much more than that, because we need more observations from James Webb, better spectra and so on, and there may well be others there. We only see these ones simply because they have been gravitationally lensed by that galaxy cluster in the foreground. They are much too faint to have been seen even by the James Webb Space Telescope without that gravitational lensing. So for other ones that are as far away, we'll have to look for other examples of gravitational lensing. But they're fascinating objects, and just you couldn't really get a more dramatic demonstration of redshift than to see the ones that are nearby, which are bright green, and these ones so far away are red. So Nick, I'm sure you have your own thoughts on that.
Yeah, I mean, the Z numbers on those are astonishing. The other thing, and it's a good question that was brought up by Mike in the chat, I mean, in terms of the mass, it's not just the mass of these. I mean, we've got 5.5 times 10 to the 8 solar masses, which is not obviously huge. I mean, we're not talking about enormous galaxies here, but their gas consumption rate is absolutely astonishing. They are burning through gas at phenomenal rates. Now, this then begs the question, is what's driving that as the mechanism for this, this consumption rate? Plus, and this again leads into, I know, an area that Abby, one of the people who, lady who introduces us and one of the people at Space Store, is really interested in terms of galaxy formation. In that, some of the early galaxies and the formation of, massive / supermassive black holes in the center, which we've seen in so many galaxies, obviously, in closer proximity, I say closer proximity, but your average galaxy, there's a lot going on in terms of, supermassive black holes in the center of those galaxies and the potential for what that can cause. It's really interesting seeing just how fast these are burning through, and what kind of stellar masses are coming out of this? Because if you've got that much gas producing that rate of stellar formation, what are you creating here? And that's the thing that obviously you can't really resolve right now with the James Webb, because even with the James Webb's phenomenal capability, when you're looking at Z numbers off the scale towards like the edge of the observable universe, you're just seeing, as you said, even with gravitational lens assist, you're seeing a blob. You're seeing a fuzzy blob. So I find this really, really fascinating. And when I first saw this story, it reminded me of, do you remember Hanny van Arkel and the Hanny's Voorwerp? Again, just looking through the SDSS data. So I've used some of the Sloan Digital Sky survey data in the past, looking for asteroids and comets. SDSS V band wasn't one of the bands we typically use, which is the green kind of filters, the V-band filters. We typically be looking in the R-band filters. You know, some of the comets obviously were a little bit easier to find using R-band. Some were obviously if they were lit up. So this data is publicly accessible. The SDSS data, anyone can go through, and it's really interesting that, you know, obviously in this case, this is professional scientists working on this, but the argument that people like the Zooniverse, etc., have put forward, you know, what the James Webb's going to be able to deliver to things like the Zooniverse project, which is galaxy classification and an identification of these stranger objects inside image fields. You know, again, because the James Webb's image fields, it's delivering image fields that we've never seen before, because it's stretching out further than we've ever seen before. So that, to me, there's so many spin-offs from this story, is what I'm saying. It's not just the green pea galaxies themselves, it's what else is happening at the edge of the observable universe. It's amazing. So again, an absolute peach of a find there, Terry.
Yeah. The amazing thing, and there's something I didn't mention really so much, is, or the interesting thing is, what size of stars are these things creating?
Yeah.
And how do they create? And the implication is that they're pretty hot and big, and with very short lifetimes. So we're very lucky to see them at this stage, actually. And if they're very massive stars, they'll be going through the supernova stage before too long. But how is such a relatively small galaxy at such a young age producing such massive stars? So really fascinating stuff.
Well, that's the thing as well. You know, objects like Westerlin 1, if the audience, anyone who's listening, doesn't know about Westerlin 1, Westerlin 1, again, has these massive stars. It's largely obscured by dust. So it's one of those things that's been picked up in the past by the Hubble in near infrared, etc. But a lot of the infrared observatories have picked it up. And some of the stars in there are absolutely colossal in terms of their mass. As we said, you know, the burn rate of this and the consumption rate, is it creating lots of smaller stars, or are we generating these absolutely enormous, we call them, you know, when I was working on Westerlin 1 project for some years ago, we called them the James Dean stars, because they were live fast, die young. They were real high burners, you know. And we go back to, you know, high school physics and Oh Be a Fine Girl Kiss Me, the spectral classifications of O down to M, etc. And the O stars, you know, really bright, really blue, really burn fast and really die fast. Thankfully, our sun is kind of in the middle in that 4 billion year lifespan. But yeah, it's really fascinating, and it leads on nicely to the next story, which again is the James Webb, but a lot closer to home, and at the other end of the spectrum, as it were. So James Webb has been sent up to do various things. One is looking at the earliest, you know, galaxy formations, looking at the edge of the observable universe. The other thing that James Webb is doing, and if we go on to the next slide, we can see that, is detection and verification of exoplanets, which is a really key part of its mission. The James Webb's mirror obviously is significantly larger than the Hubble Space Telescopes. Its its spectrographic instruments have got these micro mirrors on board that have got this ability to kind of spectrally differentiate and image lots and lots of different segments across, you know, a planetary atmosphere, for example. What's absolutely fascinating about this is that it's now verified its first exoplanet. So the TESS, the Transiting Exoplanet Survey telescope instrument or satellite instrument, had picked up a potential exoplanet around a star in the constellation of Octans, LHS 475. Now, it didn't have the resolving power or the capability to actually verify, because obviously, depending on the proximity of the star to the planet, the orbiting exoplanet, exoplanet and the orbital distance and the orbital rate that it's going around the star, these transiting exoplanets, where effectively what you're seeing as a dip in the magnitude, this is how one of the techniques that's used with exoplanets is basically you stare at the star, and if you see a dip in the star's light, it basically means that a planet could be going in front of it. That's one of the ways. The other one is wobble, basically where you're looking for the star to wobble in the spectra, or potentially even in the image, but typically in the spectra, where you see this due to the gravitational drag, as it were, of the planet as it's going from one side of the orbit to the other. The other way that's now being done, and it has been done successfully, both from ground-based telescopes to larger telescopes like the Keck, etc., obviously the Hubble Space Telescope, but this direct imaging of exoplanets, where you use basically something to occult or blank out the star's light. Now, this is the great thing about the James Webb. It has this capability within its mirror configuration, within its instrumentation configuration, that enables it to do this kind of, really selective imaging in combination with occultation capabilities that are on the telescope, and directly image exoplanets. Now, it's not done it with this one yet, but that is hopefully what's going to come from further studies with this exoplanet. Now, this one is only 41 light years away, and it's Earth-like. I mean, it's Earth-like in that it's almost the same size as the Earth. They reckon it's about 99% the size of the Earth. The downside is its distance. It's orbiting the star in a matter of days, so it's a lot closer than the Earth is. However, the star is an M-class star, so it's a red dwarf. So its radiant energy, the amount of radiation and energy it's kicking out, is significantly less than the sun. So theoretically, it could be within what's called the Goldilocks zone, which is this kind of region where, a little bit further out for our solar system, a little bit further out from Venus, a little bit closer in than Mars. Effectively, you've got this region where liquid water can exist on the surface, therefore potentially life can exist on the surface. This is the whole thing that we talk about the Goldilocks zone, obviously after the fable with the 3 bears, and not too hot, not too cold, etc., just right, as it were, with the porridge. That's why it's called the Goldilocks zone. Oh, been told my mic's a little bit close again, so I'm going to move my mic down a little bit. So this one at 41 light years away in the constellation of Oxens, as I said, is a really fascinating exoplanet, but it's not the first one, I think, or it's not going to be the last anyway, that James Webb discovered. I think this is just going to open up the floodgates in terms of what's going to be happening with the James Webb over the coming years. The question is now, is the science divide, as it were, because you've got the cosmologists and the galaxy formation fans, etc., who want to see everything out in the far reaches of the universe and look at the earliest star formation, the earliest galaxy formation. Then you've got the exoplanet people who are thinking, we've got this incredible instrument that can literally pick out specific elements in the atmospheres of exoplanets after directly imaging them, and basically prove if the planet's atmosphere is potentially dense enough or capable of sustaining life. The question then is, well, if we find a planet that's potentially in the right Goldilocks zone, could sustain life, is around the right size, has got evidence via whatever in the atmosphere of seasonal variations indicating potentially life on the surface, though not obviously a direct observation or direct evidence, what do you do then? Because even at 4 light years, we have no technology that can get there in under 12,500 years right now. And we talked about this before, but it is fascinating what the James Webb is. It's the gift that keeps on giving. It just keeps on delivering. The green peas is one thing, and being able to image at resolutions we've never had before, and capabilities and distances we've never seen before. But bringing it much closer to home, what it's going to be able to do in terms of exoplanet detection, even on there's so many nearby planets where we've probably in the past disregarded the potential for planets. But there's a lot of kind of speculation and talk now in the scientific community that pretty much every star is going to have planets orbiting it. Whether or not they've been detected due to transiting exoplanet or spectral wobble or whatever, who knows? But I think with the James Webb, it's going to open up a whole new, story, as it were. Anyway, thoughts, Terry?
Yeah, the amazing thing is that it only took 2 transits for it to confirm it. It was so definite. And the other thing is that it has an incredibly short period, only 2 days. Yeah. So it's really close in. They reckon the temperature is several hundred degrees warmer than that of the Earth. And although I haven't seen this anywhere, I would guess it probably has a captured rotation, being so close in. The other interesting thing is that they're not sure if it even has an atmosphere. Being so close in, it could have had the atmosphere totally stripped away, so it'd just be bare rock. Although apparently there is a possibility that it could be a pure carbon dioxide atmosphere, which would be quite hard to distinguish. I can't work out the physics of that, but anyway, so it's definitely not going to be a planet that we look for anything other than a very, very primitive form of life, if any at all. But as you say, it was amazing that James Webb got it so easily and was able to get the orbit and the orbital period just so easily with after only 2 transits. Normally with TESS, which I think was the original instrument that suggested that there might be something up there, and they then followed it up. If James Webb can confirm an exoplanet just in 2 orbits, that's really going to speed things up quite a bit.
But as I said, this goes then back to how much time do you then, because with the Hubble you had to do director's discretionary time, and the application backlog for time on the Hubble was years. With the James Webb, you've only got a finite lifespan with the James Webb Space Telescope anyway. I mean, it's estimated maybe 10 years. If they're lucky, they might get 15. It's all down to the cryogenic cooling. It's a near-infrared instrument and a mid-infrared instrument, so it needs to be cooled to a few degrees above absolute zero. An interesting question again from Mike in the chat. I mean, talking about James Webb and the detection, this will be a first as well, and I'm pretty sure that the James Webb will be the first thing to do it. So we've detected exoplanets, but what about exomoons? Now you think about Jupiter and the Jovian moons. We've got moons that are larger than planets orbiting Jupiter. Moons that are larger than the planet Mercury orbiting Jupiter. So if you were to detect an exoplanet and directly image the exoplanet, being able to use the same spectrographic and wobble technique on that exoplanet that you're directly imaging to see if there's a moon orbiting that exoplanet. And obviously it's going to have to be a relatively high mass ratio between the moon and the planet itself. I mean, you're not going to be detecting, something like Earth's moon to the Earth, that's obviously a very high ratio in terms of size. I think you're probably looking at something almost like a binary or a tri-system like Pluto or more. Obviously Pluto's got multiple moons now. Next Hydra, Charon obviously detected in the late 1970s. I think it's going to have to be something like that, but that's going to be an astonishing achievement if it manages to directly image a planet and then say yes, and this planet has got 1 or more moons orbiting it. The other one, and going back into Mike's question, it then opens up the possibility of edge-on-ring systems. You only have to look at the imaging capabilities that enabled us to see the rings orbiting Uranus, etc., both from ground-based and obviously spacecraft-based observations. The question then, if the ring system was significant enough and separated from the planet enough and tilted, Uranus's axial tilt is 90 degrees. So if you had a ring system, something like Saturn's, which is vastly more substantial than that orbiting Uranus, but the Uranus axial tilt on the planet that's orbiting the star, could you imagine being able to detect a ring system? I mean, we've already detected, Herschel, the Herschel Space Telescope, which is the infrared kind of precursor to James Webb. Everyone says James Webb's the follow-on to Hubble. It's not really. It's more like the follow-on to Herschel, which is quite a low resolution by James Webb standards, infrared telescope and instrument launched by the European Space Agency. Phenomenal in its own right. That detected the evidence of essentially an Oort cloud around a nearby star. So we know that around about 1 light year away from the Earth, or we theorized, and it's pretty obvious there's something there, that there's a cloud of trillions of comets kind of sitting there around about 1 light year away. And then obviously you've got the Edgeworth Kuiper belt in a lot closer, orbiting Pluto, kind of Neptune area, and then the asteroid belt in closer still, which has got some comets in it as well, let's not forget. I think it's going to be amazing. And again, with the James Webb being able to pick up comets way further out, in terms of crossing the ice line, typically with ground-based observations and even the Hubble Space Telescope, we picked up comets maybe, Saturn, Jupiter distances. What's going to be the possibility with the James Webb? Obviously, because of its spectral capability and its resolution, it's not just waiting for the comet to light up. We've detected an object that's moving, and its surface is basically a load of organics, because of the spectral capabilities of it. So there's so much. Oh, it's a joy every time the James Webb gets mentioned. It's just a joy. It really is. Anyway, moving on. Neutron stars. This one's also really cool.
Yeah, you're giving me all the very advanced physics to deal with in this one. High energy astrophysics, not exactly my forte, but anyway, neutron stars. Until I suppose black holes were confirmed, neutron stars were the weirdest objects that we knew of in the universe. They're the densest objects that we know of apart from black holes, and the density, if you want the figure. 10 to the power 17 kilograms per cubic meter. Now, I find it very hard to imagine the power of 10 to the 17. So put it this way, a teaspoonful of a neutron star weighs about 1 billion tons. Yes, 1 billion tons. It's what's called totally degenerate matter. It is so condensed that the atomic structure is totally broken down. The electrons basically are crushed out of their orbits. They merge with join with the protons, giving you a neutron. So the whole star is basically made of neutrons. There are no protons, no electrons or anything. And a typical neutron star is round about the mass of the sun, but it's compressed into a diameter or a sphere with a diameter of roughly the size of a city, say roughly 10 miles, 15 kilometers, something like that. And we've known quite a few of them. Pulsars, for example, are neutron stars that we detect from their radio signals. I'm not going to go into that. And they form whenever a very large star runs out of fuel and collapses. Giving you what eventually is sort of a supernova, the various types of supernova. It blows off all of the outer matter, but the inner core becomes an incredibly dense object, which is, in fact, it ends up as a neutron star. Now, the interesting thing in this particular case is that if the core of the star that has gone supernova like that is more than 2 and a bit solar masses, it is so massive that it will collapse directly into a black hole. A stellar mass black hole, not a supermassive black hole. If it's less than that, then it's a neutron star, and those are the ones that we see as pulsars. But what happens if you get 2 neutron stars merging, as we have in fact seen? From various things, including their gravitational wave signature. Now, if the combined mass of 2 neutron stars after they merge is below that limit of 2 and a little bit times the mass of the sun, then they simply form a bigger neutron star. If the combined mass is more than that, then that is so massive that that will collapse into a black hole. The interesting thing is what happens in the interval between the merging and they collapse into the black hole, because it's not instantaneous. It's very, very fast. And this is one of the amazing things about science. People predicted in advance what would happen. And then, lo and behold, we get the observations which confirm it. So what they reckoned was that as they merge, the 2 big neutron stars merge, and these are ones that are bigger than the limit where they will eventually form a black hole. You will get oscillations as they merge together. They're obviously spinning very, very fast, milliseconds, thousands of times per second. And they will produce oscillations. They looked for these oscillations and couldn't find them because initially they thought that they would be periodic. In other words, a regular, like a sine wave. Then somebody did a little bit more research, calculated sort of the speed and the rotation period of the neutron stars as they merge, and said, no, they're not going to be periodic. They're going to be quasi-periodic. In other words, it'll not be an exact nice waveform. They looked again at the data and they found these quasi-periodic oscillations. So we'll have to go to my notes to see the next bit of this. So this was Cecilia Chiarenti of the Goddard Space Flight Center, University of Maryland, and also University in Brazil, obviously very talented. What she did and her team did was they searched through BATSI data, and I've just lost my screen, so I'll try and come back here. Okay, that's better. They searched through the BATSI data, that's the burst and transient something experiment, transient can't remember the days, but that was on the Compton Gamma Ray Observatory, very early, well, not a comparatively early satellite looking in gamma rays, now defunct, but they looked through the old data and they found these quasi-periodic oscillations. Now, this is where sort of it's the sort of intensity and accuracy of the science that blows your mind. They reckon that it would have a period of about 1.5 milliseconds. That is the period at which this thing merges. It would last for only a few hundred milliseconds in that state before it would collapse into a black hole. So you have to see this thing, which exists only for a few hundred milliseconds. They searched through the data and they found the evidence. So they reckon, as I say, this one that they have found ended up as a hypermassive neutron star on 4 solar masses, existing for only a few hundred milliseconds, and then collapsed into a black hole where we couldn't see it anymore. Now, that would produce gravitational waves. They know that. Unfortunately, the gravitational waves of that sort of event are too high a frequency for our current observatories to be able to detect. They won't register anything with that frequency. The next generation of gravitational wave detectors should be able to detect that, and hopefully in the future there may be other examples of that. But it's a beautiful example of scientific theory predicting something, then you go out and look for it and you find it and you confirm it. So brilliant stuff.
It's astonishing. And, going back to that duration, these things are spinning at 78,000 revolutions a minute. It's just ridiculous. And it's double the speed of the fastest pulsar. And we go back to pulsars and Jocelyn Bell Burnell in the late 1960s, getting the Nobel Prize stolen from her by Anthony Hewish, etc. Horrible story that is. But pulsars, obviously, we were able to, time these things so accurately, and they are like this remarkable clock, the little green men, as they were initially thought. This thing's double the speed, and they reckon that they can only sustain themselves for that duration due to this spin rate.
Yep.
Basically, it's stopping the collapse. This ridiculously high spin rate. I mean, 78,000 revolutions. You can't even imagine that. It's this is something, as you said, this is a stellar mass object, or 2.5 times stellar mass object, but rotating at hundreds and hundreds of times per second. It's just off the scale. But and as you said, the duration of it, I mean, you only have to go to CERN and look at some of the particle collisions there. The time duration that they last for is in the micro, nano, picoseconds, etc. We're looking at things on a whole other scale here that are doing the same thing. They're literally just annihilating each other and/or forming black holes and/or collapsing into larger, more massive neutron stars. And then again, retaining these. Blows my mind.
There's a question there: how is it possible without even ripping themselves to pieces? It's simply the gravity. They are so dense already that the gravitational force is strong enough to hold them together. They may well be elongated, egg-shaped. I haven't seen anything either one way or the other on that, but I would be quite surprised if they weren't slightly egg-shaped. And therefore, obviously the merger isn't instantaneous, because these are objects, as we say, approximately 10 to 15 kilometers or miles. At that scale, it doesn't really matter. So they cannot merge just absolutely instantly. There comes a point when the surfaces touch, but the surface is, is not the center of the object, let alone the opposite sides. So it takes a little while for them to merge completely. But again, the gravitational pull, because there's simply so much matter there, so much mass, that it pulls them together so quickly that they don't get a chance to fly apart.
And that's the thing. You look at the orbital distance between them as they're approaching each other. You're getting this intense and very rapid increase in the gravitational field, which is going to create not so much the kind of oblate spheroid, as it were, but almost like an egg shape. You're going to get the two nearest points kind of being drawn more to each other, almost creating like a dumbbell type shape that we've seen with some comets. To be able to see that would be remarkable. Obviously, we're probably never going to see it, because these are objects that are.
It'd be nice to see it, but you wouldn't want to be too close.
You wouldn't want to be anywhere near it. I mean, the event around the Schwarzschild radius, I mean, that's black hole. We're going into black holes.
Well, the burst of gamma rays would do it anyway.
But that's the thing. The GRBs, and the science team that went and looking for this looked at 700 short GRBs. I mean, this is the thing. Now that we've got the ability with gravitational wave detection to hunt back through all this old data. As you said, Compton deorbited 20 odd years ago. I mean, you only have to go back to IRAS and some of the data that IRAS was detecting in the 80s, as it were, that's now coming to the fore and being revisited by the likes of James Webb with its incredible resolution and capability over what IRAS had. Yeah, it's an evolving story. It's a constantly evolving story. But as you said, the GRB, the energy from that, it's just insane. I mean, that's the thing. Gamma ray bursts. If you want to know about the deadliest things in space, there's a talk at Marlborough College in Wiltshire in a few weeks, which is going to be talking about the deadliest things in space. GRBs are right up there. They're not fun. Anyway, what is fun is looking up. So hopefully you got a telescope for Christmas, or you've treated yourself to a new telescope, or you've dusted down your old telescope. You've been a bit inspired to look at the sky, and there's some good stuff coming. I'm one of these people that I've spent years imaging every galaxy, nebula, whatever. And my main passion, as Terry knows, is comets. It always has been comets. And thankfully, we've got a new comet. So C2022 E2. Snappy name. They're named basically after the year and the month and the time in the month when they're discovered, is coming around. Now, there's a lot of hype. If you read some of the major newspapers in the UK, it's going to be this great big bright comet. Well, it's not. It's not going to be Hale-Bopp. It's not going to be, as Terry was saying, Hyakutake or any of the great comets of yore. Hale-Bopp was the last massive one that I guess most of us may remember from late 1997, etc., because it had such a high inclination. It was such a massive nucleus. It was about a 30-kilometre nucleus, and a fantastic comet to observe. You could see it from the centre of London. It was so bright. It's not going to be like that. Some of the press are saying you can already see it. I challenge anyone to see this naked eye right now, unless you are Stephen O'Meara watching this show, and he's a notable astronomer and observer who's known for his remarkable vision. He can way surpass the Mag 6 limit that most of us have got to. I've got a really dark back garden here where I'm in Wiltshire. You can't see it. You can see it with binoculars. If you've got a nice little set of binoculars, it's very easy to pick up. And the great thing about this comet is it's relatively high in the sky. So it's going to be one of those that's going to be there for a good few weeks. It will kind of touch around naked eye visibility around about magnitude 5, 6. A good set of binoculars, you're going to be able to see it. I've seen some great images from amateurs already. Little fuzzy tail. It's not the huge tail that we saw with Neowise, not yet. And that's the thing with comets, they're unpredictable. You have no idea what they're going to do next. So it could remain like a fuzzy little blob and a little bit of a tail. It could go spectacular. We only have to remember, when Terry and I were talking about this just before we came on air, Comet McNaught a few years ago, where Northern Hemisphere, it was a fuzzy little thing. It gets into the Southern Hemisphere, lo and behold, whoosh, massive long 2.5 kilometre, 250 million kilometre tail, loads of striations in it. It was amazing. It's not going to be that, we don't think, but who knows? In a couple of weeks' time, we could be saying, yeah, look, there's this huge comet in the sky. That's one of the things, Terry. I don't know, are you excited about that one?
Yeah, it's the best one since Neowise, which was reasonably naked eye if you had a dark sky, not nowhere near as spectacular as Hale-Bopp or Hyakutake. The thing is, if you go out just and look up into the sky, you're not going to see this even with binoculars. You'll be sweeping all around the sky in your binoculars. You will need a chart to show you where it is, or an app or something. There's Sky Portal, for example, which you can use. There's Heavens Above. There are various ones, but you are going to need to know where to point your binoculars or your telescope. Otherwise, you simply won't see it. It'll just be at a quick glance, it'll look like a star. Only if you sort of focus on it for a while and look more closely, you'll see, well, it's not a star, it's a little fuzzy blob. So you will need a chart or some sort of IT aid to actually find it. Then if you have a telescope and you can use a bit of magnification, you'll maybe see a bit of structure, you see the tail. The thing is that you will be seeing on the internet, if you're interested in this, and even in the papers and maybe even on the TV, photographs showing a really spectacular object. Those photographs record more detail than you will see with the naked eye. You may not see the green color at all. CCD imaging is very sensitive to green. Similarly, just to sort of digress slightly, if you see photographs of aurora that you may see it now coming up to solar maximum, those ones are probably not that spectacular to the naked eye. But getting back to the comet, yeah, the best one we have at the moment, the best one we've had for quite a while, it's moving up, well up into the northern sky. For example, an easy way to find it, on the 30th of January, it will be in a direct line from the pointers of the plough and Polaris. So in other words, if you're trying to find Polaris by taking the line from the pointers up to it, 2/3 of the way along there on the evening of the 30th of January, you will see it there just 2/3 of the way up to Polaris. In February, it passes very close or quite close to Capella, one of the bright first magnitude stars, which is an easy way to locate it if you haven't got one of these apps. But basically, yeah, find a way of locating it exactly. It's passing through an area of the sky where there aren't very many bright stars. Draco, Ursa Minor, although on the 25th of January, it passes not too far away from Kochab, the second brightest star in Ursa Minor. Then it's up in Camelopardalis, which is one of those big, vague, sprawling constellations with no significantly bright stars at all. The 28th is close to Kochab, which is Beta in Ursa Minor. So you will need some sort of an aid to show you just where to look. And if you have a decent pair of binoculars or a telescope, you should get quite a nice view. It'll be coming to its best just after our next one of these Space Store Lives, which is the end of January, and it's due to be closest to the Earth on the 2nd of February. So we'll be able to update you then, but certainly have a look between now and then with some help to show you just where to look.
Yep, absolutely. And there's a comment in the chat from Rachel, Daydream Astro, who is quite a prolific imager, and I know the kind of equipment that she's been using, and it's not spectacular. So it's one of those don't believe the hype, as it were.
Yeah.
The people in the news and the press are going to be talking about this amazing, spectacular comet. We were talking before we came on air about Comet Kohoutek in the early 1970s, and the fact that was going to be, Terry will remember this one, was going to be spectacular and enormous, and the only people who got a decent view of it were those orbiting on Skylab. So, yeah, definitely don't believe the hype, as it were. ISS, we've got loads of ISS passes to look out for. It's one of those, again, using, as Terry said before, Heavens Above is a great little app, or if you've got an iPhone app or an Android phone app, you can literally just hold it up to the sky and it will tell you where things are, and it will also give you can get even Raspberry Pis, these little pocket computers. You can build systems that can give you an alarm that says when the ISS are going to be flying over you. It's always fun to take the kids out, in particular if you've got the ISS flying overhead. It's not that wonderful a thing to see, but it's just nice to remember that there are people up there that, it's one of the few places left on the planet where the Russians and the Americans are happily shaking hands and collaborating and making cups of coffee for each other. So one of those things to see. We've got Venus as well, Terry.
Yep. Venus is moving out from the sun now in the southwestern sky in the twilight. In another couple of weeks, it'll be much easier to see and really lovely in the spring. But it's going to pass very close to Saturn. We were getting excellent views of Saturn in the autumn. It's now slipping down into the evening twilight. But on the evening of January the 22nd, Venus is going to pass quite close to Saturn, an easy chance to locate it. 23 arc minutes, and that's just about 2/3 of the diameter of the moon. So if you have a clear sky the evening of the 22nd of January, Venus will be more or less unmistakable. It's so bright. And look just above and to the right of it, only 2/3 of a moon diameter away, you'll get your last view of Saturn. So it's nice to see these conjunctions, not of any great scientific value, but they're just interesting to see.
If you've got a good wide field imaging system, those kind of diameters are perfectly doable with short focal length refractors, etc. You may be able to see both the phase of Venus, if you're clever with your imaging and clever with your techniques, being able to see the phase of Venus and also the rings of Saturn in the same image, which is going to make it a really nice image if you're that way inclined.
Well, Venus will be about 93%, nearly full, so it'll be quite hard to see the phase in
any
that
form
one.
of phase.
If it was in the crescent phase, yes, very definitely you could.
Yeah, absolutely.
But definitely have a look and watch out for the ISS, a free show every night for the next couple of weeks.
Absolutely. And, talking to free shows, when things deorbit, we always get to see a great free show. Somebody off the coast of Tenerife got a really great free show from Virgin Orbit a few weeks ago. So enjoy. Anyway, just before I pass back to Abby, we've got to say a big thank you again. This is our kind of third year of doing this. It's third year of doing this now. And we've had so much support from the Space Store. It started off as a little idea that we had to kind of do a bit of a radio show, be a bit irreverent, be very unlike some of the other shows that go out there, although some of the other Astro podcasts have been quite irreverent about Virgin Orbit this week as well. But quite irreverent, but we do it with a bit of fun, and we hope you enjoy it. thanks very much for supporting us. Massive thank you to Space Store. Visit the Space Store in Oxford. It is really, really cool. They've got some amazing meteorites there as well at the moment. And it's just a short trip from where I am. So I'll hand you back to Abby, but definitely see the Space Store.
Thank you. Yeah, thank you for another fascinating show. I mean, more incredible stuff from James Webb again. I think at the rate it's going at the moment, it might end up in every show. I mean, I hope it does. It's really good science. Anyway, yeah, so check out our opening times online and do come down and see us in Oxford and also in Didcot. We've got shoppers there as well. Lots of great virtual reality experiences and, as you say, meteorites and stuff to come and have a look at. Our next show will be in a fortnight on the 31st. So in the meantime, subscribe to our social media channels to stay up to date with what is happening here at Space Store. And thank you again to Nick and Terry, and thank you to everyone for watching.
Happy New Year. Happy New Year to everybody.
Bye.
Cheers. Bye-bye.
Bye. Hi, my name's Nick Howes, space enthusiast, author, writer, broadcaster.
Hi, I'm Terry Moseley, past president of the Irish Astronomical Association, lifelong astronomy and space nerd, absolutely fascinated by everything, both man-made and natural up there.
So every 2 weeks, Terry and I give you the latest, hottest news from space and human spaceflight, robotic spaceflight, and what's happening up in the skies. Please tune in to us every fortnight with the Space Store. Adios, amigos.
Bye all.